In the last class, when we were discussing the effect of corrosive media on fracture toughness, and the plot you see on the left hand side comes from multi-specimen testing. Okay, so you load a lot of specimens, and this is a normal fracture toughness test. So you take your specimen, put it in corrosive media, and then you let it be there as long as it breaks. Okay, so catastrophic failure happens, and you plot that. So with increase in time, the fracture toughness appears to be decreasing, and there is a value below which, if you put for enormous amount of time, for a very large amount of time, even then there will be no failure. So it is similar to what you saw in fatigue, endurance. Okay. And then we also discussed about modified CT specimen, and we have also seen a video of this kind of CT specimen which was used in a fixture, and you can do all the instrumentation with this. So you can put a COD gauge where you see that COD knife edges are there, and take the wires out and seal the wire so that it is not affected by the corrosive media. And but then there is a problem that the corrosive media should not affect the loading screw which is there. Okay, so you have to make a material which has a coating, protective coating, or it's a material which does not show corrosion to the media where you are trying to put or planning to put your specimen. And with one specimen of this kind, you can find out the threshold value of K1C, so which is K1 EAC or K1 SCC, stress corrosion cracking or environmental assisted cracking. Environmental assisted cracking is a vague term because environment can also include temperature. So, but those things are, we are not talking about that because those things are a separate field, and we know what happens when you change the temperature. And because there are chemical reaction involved in corrosion, you will have the effect of free energy and you will have the effect of Le Chatelier's principle. Okay, so changing temperature or pressure will change the reaction rate, and that will change the rate of crack growth. Okay, so then what we have studied in the previous slide is that from K1C the value degrades to a lower value which is K1 EAC. Okay, and between these two values the material can show stable crack growth. Okay, once it reaches K1C, then it will show catastrophic failure, and once it is beyond the threshold value of EAC, it will be stably growing. So that's the plot on the right hand side, and when you plot semi-log, it's a not semi-log, it's a double log plot. So crack growth velocity versus K. So for a certain value of K there will be no effect of crack growth. Okay, and then the velocity will increase, and then it will become stable, and then it will become unstable. Okay, so this kind of graph we have seen before. We have seen it in fatigue. Okay, dA by dt versus, what was that plot? Delta K. Okay, in this case it is K, and we have also seen similar graph in creep where this graph will be shifted to the origin, and it will start with a positive value. On y-axis you will have strain, on x-axis you will have time. Okay, on the left hand side what you see is the effect of cyclic loading on it. So scenario can be further complicated. It can be creep, it can be creep fatigue, it can be environmental assisted cracking in presence of cyclic loading. You can further complicate it by putting it at high temperature. Okay, so very small amplitude of loading has been applied on the curve which has a steeper slope, which is lower than the static curve. So the maximum load is P and the minimum load is 0.9 P. Okay, so R is 0.9 in this case, and you see that there is a drastic change in the K versus time to failure plot. Okay, and percentage degradation has been formulated in this form, where delta K TH is calculated by Kmax minus Kmin. If you are going in opposite direction, reverse direction, then that K minimum will be for zero stress. Okay, so you shouldn't count the reverse stress that we have discussed in today. Okay, so and then we have the effect of temperature and effect of pressure. So on the left hand side, you see that as the temperature increases, you will be going on this side on x axis, and as that is decreasing, dA by dt is increasing. Okay, so the temperature will affect also the chemical reaction, the activation energy of the chemical reaction, as well as the material property. So even if you don't have corrosive media, the yield strength and strengthening mechanisms will change as you go lower in temperature. Okay, and then on the right hand side, you have the plot of pressure versus dA by dt, and as the pressure is increasing to 1 atmospheric pressure is the maximum. Okay, and as it increases, dA by dt is increasing. So this is the test at room temperature, and on the left hand side in this figure you have a dA by dt correlation in the form of Arrhenius equation. Okay, so dA by dt is directly related to the rate of reaction, and that has an activation energy dependent on temperature, so you have that Arrhenius type of equation. As long as the activation mechanism, so the mechanism of reaction is not changing, your activation energy will also not change. Okay, done. Yeah, so the syllabus is over. And I will introduce one more thing which is not related to the syllabus. It is just for thinking. It is out there in media and on YouTube, and there are a lot of information about this, but I don't know how many of us think about it. So I'll just talk a little bit about that, even though I don't understand this completely. So there is a case of, these kind of things have been applied in various regimes, but one case which I can talk about is the case of population. It can be the case of population of human or animal or insects. Okay, so if you take two animals and then let them reproduce, rabbit multiplies